Okay, thank you. So I'm going to build up upon what Rami gave earlier today of harness-based verification. So I'm going to touch on Kani from a different angle, which is contract-based verification. And usually people say, I hate to be the person between you and lunch. So my talk is after lunch. I personally hate talks after lunch because I'm pretty sleepy. But hopefully you guys I can keep you awake. All right, so this is the agenda. So we're going to talk about a recap of Kani, talk about contracts, what are the different types of contracts that we support in Kani, the semantics of those contracts and how they can be used. We're going to go through a bunch of examples. So to recap, this is the Kani architecture that was Rami touched upon earlier. So Kani takes in a Rust package, and it has a cargo wrapper, similar to what Caron does, for example, which compiles the main crate and its dependencies through the Rust C front end, and it takes the mirror, translates it into this intermediate verification language called GoTo, which is the language of CBMC, and then it calls CBMC under the hood, and it does some post-processing of the results that we get from CBMC. So we don't post the output from CBMC verbatim. We go through some post-processing because we have some internal properties that are intended to improve or enhance the user's understanding of the results. So those get bundled up with some of the main properties when we present the results. If you haven't already, I encourage you to try to install Kani. You might be able to follow along with some of the examples I'm going to give a bit later. And installing Kani should be pretty simple. It should work on most platforms. If it isn't, please file a bug. I know we've had issues with some operating systems in the past, but hopefully we are in a good shape at the moment of support. So in terms of contracts in Kani, so contracts are implemented like many other tools as procedural macros. That's usually the most ergonomic in terms of allowing the user to specify them in their code. And the current type of contracts that we support are function contracts, loop contracts, and type invariants. So I'm going to go through each of them in more detail. So function contracts, like many other tools, we have preconditions that can be specified as Kani requires with a certain Boolean expression. We have postconditions that can be specified using Kani ensures. And for the ensures clause, what we found to be useful is to provide a closure. So essentially, you implement a closure which takes the result, the return value of the function as a parameter, and you can specify the postcondition in terms of that return type or return value. And finally, there are modifies clauses. I know modifies clauses are not something that are first-class citizens in every verification tool, but due to the way we do things in the underlying reasoning engine CBMC, we do rely on modifies clauses quite a bit. So now to somewhat a surprise is in order to use contracts, you still have to write a harness. So even though the title is contract-based verification, compared to Rami's earlier talk on harness-based verification, every verification entry point in Kani has to be a harness. But here the harness annotation is slightly different, whereas previously any harness would be annotated with Kani proof. If you want to verify the contract of a function, you specify that using proof for contract. So if you have a contract for function foo, then you write proof for contract foo. And you might ask, why do you need a harness in the first place? Why is the contract insufficient as an entry point by itself? The reason we went with this design decision is that oftentimes we want to allow the user to do a constructive creation of the inputs to the function, as opposed to specify the function, the inputs using first order logic or a predicate. So essentially, both ways are allowed. You can either specify the constraints on the inputs of the function, the input parameters, or you can construct them imperatively using in this function, in this harness function. So for things like the example that Remy mentioned earlier, where we have the small vec, it's sort of difficult to specify the validity, the type validity of this data type. But in terms of constructing it, it's not very difficult to do that using allocation and so on. And once we verify the contract, if you want to use this contract, we have this annotation called Kani stub verified. So let's go through a quick overview, an example. So essentially, if you have a function foo that is annotated with its contract, requires, modifies, and ensures, then if you want to verify this contract actually holds, then you write a harness, which you can call whatever you want. In this case, I called it check foo contract, and it has to be annotated with proof for contract with the function it's verifying. In this case, it's foo, and of course, the harness has to be calling foo itself. If it doesn't, Kani is gonna throw some bad language at you. Now, once we verify the contract, if you have another function bar that calls foo and you would like to verify the contract for bar, then you write a harness for bar, which has proof for contract bar. But notice the stub verified annotation on top of the proof for contract, which says when we're verifying the contract for bar, replace foo with its contract. And again, if there is no contract for foo, in this case, Kani is going to complain and say, hey, you say stub verified, but there is no contract that verifies foo in your module. And so it's going to point this out to prevent people from shooting themselves in the foot and relying on something that might not be proven. Yes?
So what would be the motivation for not putting stub verified foo on any contract that isn't the contract for foo?
Good question. I'm gonna get to that in the next slide. So, so a couple of things regarding contracts in Kani. The first is that contract annotations are optional. So you don't need to annotate every single function with its contract. And if you don't have a contract for the function, then this function gets inlined, which is kind of like the harness-based verification that Remy was describing earlier. So this gives the user flexibility in which functions they want to write contracts for. And one point here is that oftentimes the specification for a function could be way more difficult to write than the function implementation itself. If you're like the first order logic specification of a function could be quite complex, in which case you don't need to write a contract simply, and this function is going to be inlined. So this is the first remark. The second remark is what you were asking about, is contract stubbing is currently opt-in. This is debatable. We within the Kani team itself, we don't have full agreement on that this is the right choice. Maybe we can have a switch to change whether it's opt-in or opt-out. But essentially, the point is that this gives user the full control of whether they want to use a specific contract during verification or not.
Do you know a specific use case where that would be a motivation?
Yes. So one specific use case is that sometimes the contract might not be the full specification of the function, but you want to use this contract for verifying, some other complex piece of code. But in some other contexts, it's okay to inline this function. And actually, if you use its contract, you're not going to be able to verify because it's not strong enough. The post conditions are not strong enough to imply some other piece of code that you want to verify. Does this make sense?
I could follow on.
Okay, maybe the example I have might touch upon this a little bit. Okay, so in terms of the semantics of contracts, so the semantics of the preconditions and postconditions and modifies clauses depend on the context they're in. So let's assume we have a function foo that is annotated with a contract. Now, each of those constructs are going to, or each of those annotations are going to behave differently depending on whether this function foo is specified in a proof for contract harness, or it's specified in a stub verified harness, or neither of those. So more specifically, requires clauses are assumed in a proof for contract context. They are asserted in a stub verified context, and they are asserted if you have, if the function is neither mentioned in a proof for contract or a stub verified. And the reason we do this is because we want to verify that the preconditions hold if you're calling the function, even if you didn't explicitly require, you don't explicitly stub this function with its contract. We still want to verify that the precondition holds. The common issue we ran into before is cases where the precondition is over-constrained, essentially, is too strong, which makes the, verifying the contract go through, but actually this precondition might be too strong for the callers. And in this case, having it as an assert that is always enabled makes it possible to catch those issues where you've specified an over-constrained precondition. For ensures clauses, postconditions, they are asserted in a proof for contract context. They are assumed in a stub verified context, and they are also asserted otherwise. For function body, as you would expect, it's included if in a proof for contract context. It's omitted in a stub verified context, and it's included if in the otherwise. Lastly, for modifies clauses, what we check is that only variables that are mentioned in modifies clauses are actually assigned in this function. So if this is not the case, then verifying the contract is going to fail. We say there's this variable that is assigned by this function, and it's not mentioned as part of the assigns clauses. So why do we need to verify that? Because when we replace the function with its contract, we're only going to havoc the variables that are mentioned in the modifies clauses. So if it's not mentioned there, then we're not going to havoc it, meaning that you could have vacuous proofs or soundness issues. Yes?
Why do you need to have the modifies clauses? Why can't you do something like all the variables which come through mutable roles, behavior,
Yes, great point. With Rust type system, as many people mentioned earlier, we should be able to infer that, and that's what we're planning on doing. We're not there yet, so you have to specify them manually, but that's absolutely correct. Okay, so let's go through a quick example. So here we created a class or a data type called fraction that represents a fraction. So it has a numerator and a denominator. And I've implemented a function, a method for this data type, which is called simplify. So is meant to simplify the fraction. And what it does is it computes the GCD of the numerator and the denominator, and then creates a new fraction that divides each of them by the GCD that we just computed. So let's say we want to verify something about this function, this ensures clause, which says that the resulting fraction is equal to the input fraction. And the equality here is not defined in the usual sense that both the numerator and denominators are equal, but it's defined in the sense that the fractions are equal. So 10 over 5 is the same as 2 over 1. Those are equal. So we want to verify that this function maintains this behavior or meets the specification. And what we would do is specify the contract for GCD. In this case, this is the contract that is shown here. You don't need to look at the if. This is just a special case where both inputs are zeros. But in general, the result is not zero, and it divides both the x and y. Now, This is not a complete specification for GCD because it only says that the result is divides both inputs, right? But it doesn't say anything about being the greatest common divisor. However, this is a case where for the property that we want to prove, this is sufficient of a contract to imply the property. So we don't need to provide a full specification in this case because it's sufficient to prove the property that we're interested in. And so this touches upon what you asked earlier, Just in this case, we might not be able to use this contract to verify other properties that require the stronger specification. So now how do we prove that this contract holds? We write this little harness right here that says proof for contract GCD, and then we call GCD passing Kani any, which is essentially Havelock values for the inputs. And I can run this quickly. So this is the, oh, it's not sure. So this is the GCD function right here, and it's the implementation and its contract. And what I can do is run cargo Kani, check GCD contract. So this should come back in a few seconds and tell us that this contract actually holds. And yep, verified successfully. And it did a bunch of checks in between. Kani automatically instruments checks like dereferences and out of bounds accesses and so on. Yes.
I'm wondering why we have the check. Can you go back to the check, the slide you had?
It's right at the top.
We have check GCD contract here, which is basically just a wrapper saying, go and verify the contract that you wrote on the GCD function. Why do we need that at all? Like, could we have just say, use the contract or something?
Yes, you're absolutely correct. So we currently have to have write a harness, although we're working on eliminating the need for a harness in cases like this, which is a trivial harness. But we still want to give the user the ability to construct the inputs in cases where, here the inputs are completely non-deterministic, but there are some cases where you need to maintain some type invariance and would need to construct the input parameters imperatively.
So in that case, if you say you had a more complex setup you had to do and build a more complicated data structure that you're going to push into the function, how is the contract or the summary then actually? Oh, the contract is still written on the function itself, and so it's still okay. So then you're just building like an SMT formula or a go-to formula that just asserts that the outputs are what are expected and using that in place of the actual symbolic execution.
Correct. Yes. Yep. Okay. So once we've verified GCD, now for the main function that we wanted to prove, which is the simplify method of fractions, we can write another harness that says proof for contract fraction simplify. And here, what you see highlighted in yellow is that we're going to stub the GCD function with the contract that we just proved for it. And the harness, again, is pretty simple here. It just instantiates the input parameters with non-deterministic values, calls the simplify function, and that would verify the contract holds. Now, again, coming back to the point that Just mentioned, is we actually don't need to stub this function, GCD in this case. We can actually directly write a proof for contract for fraction simplify without stubbing GCD. So this would work in Kani. Here, it's a simple enough case. We would need to increase the unwind value. As you can see here in the, let me bring up the Visual Studio again. So those are the two versions, the stubbing, the version with stubbing and the version without stubbing. And one of them, the unwind value that I had to specify, was lower because we don't need to look at the body of GCD, which has a loop or could be implemented recursively. And in the other case, the unwind value had to be larger. But both of them are possible in this case. The one without stubbing is going to take longer. In my runs, it took about double the time to verify, but the option is there essentially. But yeah, I would very much like maybe an option that would stub everything that has been verified automatically, and you would opt out if you want, as opposed to opt in. That would make a lot of sense. Okay, now, so this was an example of using contracts for verifying functional correctness. But one of the things that Kani, one of the reasons Kani was created in the first place was to verify unsafe code. And I wanted to show an example of using contracts to verify unsafe code. Rami alluded to that Kani is being used to verify the Rust standard library at the moment. AWS actually created a contest for this purpose, which many research groups have been contributing to. But the reason we want to verify something like this is because even though a lot of functions are safe, like this function that you see here on the left, split vector, but underneath it calls a split at mute, which is a safe abstraction. So the function split at mute itself is safe, but it has an unsafe block. So essentially, even though the user level code is strictly within the safe subset of Rust, but we still have, if something is wrong and this unsafe block inside, then the entire, trusted code base is completely destroyed, essentially. And so this is why we would like to use contracts to verify safety as well. One of the, we tried to extract some statistics on unsafety in the standard library. And even though the majority of functions are safe, which is the sum of the two columns on the right, those are safe functions, but the subset of the functions, safe functions that actually have unsafe, they call unsafe functions, is actually, this pink bar right here. So the majority of functions, safe functions, are actually, call unsafe or have some unsafe underneath them. So this is an example of a contract that is annotated in our fork of the standard library. So this is a function add in part of the non-null module, which is a wrapper for a pointer that is guaranteed to be non-null. And we can essentially directly map the preconditions of the functions that are specified in the documentation to the contract that you can see here. So for example, the safety conditions, the first of which says the computed offset, which is the count multiplied by the size of the type T, must not overflow iSize. And this directly maps to the first two lines of the precondition right here, that count dot checked mul is sum, so it doesn't overflow. And when we actually perform the multiplication, it has to be less than or equal to iSize max. This is a requirement for the majority of things that deal with memory in the Rust standard library, that they have to not overflow iSize max. And then the second requirement is that if the computed offset is non-zero, then self and the self plus the pointer, the offset essentially, have to be pointing to the same allocated memory. And this is what the second clause or second conjunct in the precondition does. It essentially uses this predicate that Kani provides, which is called same allocation. And this predicate asserts that the pointer as well as the computed offset pointer, they have to be part of the same allocation. So this is a predicate that is implemented essentially internally to check that this is the case. And this relies on the memory model that CBMC provides. This is another example. I can skip further up. Now, the other type of contracts we have in Kani is loop contracts. And basically, those you can annotate a loop construct with Kani loop invariant and some expression. So for example, you have a while loop, and you can write on top of it Kani loop invariant and some predicate in there. And what we currently support in Kani is while and loop loops. We don't support for yet. And we have a PR open that adds support for quantifiers in loop invariance that is about to be merged. So hopefully with the next release of Kani in a couple weeks, we would have support for quantifiers and loop invariance as well. So how do we deal with loop contracts? Essentially, we check that the base case holds, meaning that the invariant holds before the loop executes, and that the invariant holds after executing an arbitrary or one step of the loop starting from an arbitrary state where the loop invariant holds. So same semantics used in many other tools. Last thing I wanted to talk about is type invariants. And these are specified using safety constraint, Kani safety constraint, and a certain condition. So the example I'm showing here is a structure that is representing an unsigned integer that is a modulo 100. So essentially, its range is from 0 up till 99. And the way you can specify this is you can annotate it with safety constraint and say x is strictly less than 100. And how Kani treats this is that it would actually, when you derive arbitrary for this data structure, we would make sure that we satisfy the safety constraint. And we also provide a trait called invariant. And if you derive this trait, it provides a function, a method called isSafe, which you can use to check that after executing every method of your class, the invariant is still maintained. So the code that I just went through, the GCD code, is actually available on at this link. If you guys want to clone it and try it out, would be happy to have you try Kani and report issues or ask for help while we're here. And that's pretty much what I wanted to go through.
Any questions? Maybe we bring up the size of the questions.
Okay, so just want to ask, so with, really interesting, really impressive, having to come up with all these constraints, and I mean, it's really interesting. But the question is, so with this kind of verification, I'm just thinking from an empirical software engineering perspective, right? Do you have an idea of like what kind of properties that are common that are like Kani is being used to correctly verify beyond just memory safety properties? And okay, I also know that AWC Commons verify some data structure correctness properties. But what kind of other properties do you guys use this to verify as well? I don't know if there's some data on that somewhere.
Yeah, so Remy touched upon that in his talk earlier. So we have, Kani is used, across various teams at AWS that use Rust, and their usage cases are, I would say, could be, on a big spectrum essentially. So some of the code bases that we've dealt with are heavily using unsafe because their performance have a lot of performance critical portions, and they wanted to verify that all their unsafe is actually safe. So they're using it to check that there are no null pointer dereferences or out of bound accesses and so on. But we also have some usages that are more on the functional correctness side of things. So yeah, it's all over the place.
Okay. Yeah, I would be really interested in maybe that chat on some of the functional properties because I've always wondered those kind of the functional properties, and I think it would be interesting to see many of the functional property use cases as well. Yeah, but thank you.
Yeah, we have
Oh,
Just
yes.
executed simplify, but there was no actual contract.
Yeah, so this is the contract. The devil is in the details of this equality, because equality is for fractions is a bit involved but essentially one thing that I wanted to point out is if you want the full correctness specification of simplify, which is this commented out line right here, which says that if it actually simplified, then the GCD of the numerator and denominator has to be 1, right? And this, if we were to enable this post condition, then the property that we verified for GCD is not sufficient to imply this. So in this case, we wouldn't use we wouldn't stub GCD with its contract unless we prove a stronger contract.
So yeah, I see you're starting to have quite expressive contract elements. For example, you showed that you have type invariance. And so Kani is starting to look more and more like a full-fledged Polar verifier. So I was wondering, what is the limit? Like, what is its scope? Do you want to go that way, or do you want to stop before?
Great question. So essentially, we want both. We want to give user the ability to verify the way they want. And what we've seen with CBMC, our experience with CBMC for many years, is that even though CBMC shines at what it does, but people want to use contracts and they want to use unbounded verification and things like that. And so we're starting to transform Kani towards this, and people can use it in whichever way they see possible. But we want to go all the way to supporting contracts with quantifiers, with and interactive perhaps. And that's the reason we've been working on integrating Charon is allowing people to also do interactive theorem proving through Lean, for example, if they're interested in.
So just a follow-up question to mine. So I'm just looking at, there are two Kani ensure statements. The one is commented, one is not commented. Are there efforts? So I know, for example, there's the AutoVerus paper that tried to automatically generate loop invariants, for example, to aid this. Are there efforts in your team or within that tries to find ways to infer a function's expected property or correctness property by looking at the function and coming up with these ensure statements?
Yes, there are efforts. In fact, we're specifically doing that with a standard library verification. And just a few weeks ago, we created something that would automatically infer the contracts for many of the standard library functions. And this is where, through this automatic generation and verification, we were able to find a lot of issues in the standard library that we're currently investigating. Some of them are, arguably not issues because they find issues in private functions, which developers might argue that these are not meant to, they do have preconditions because they're private functions and things like that. But yes, that's LLMs are amazingly good at inferring those types of things. Specifically for the standard library, there is a requirement that every function, unsafe function, is annotated. It has a documentation that says the safety documentation, essentially. And because this exists in natural language, it's easy for the LLM to go and translate that into a specification.